he has many memberships in professional and honor societies. Okay, and also he has many special awards. So let me start.
Good afternoon, ladies and gentlemen. My name is Gülay Özkan from Department of Chemical Engineering in Ankara University. Special thanks to Professor Yasemin Çiftçi and her team for their contribution to prepare this Congress. There are 7 presentations in this section. I kindly ask the speaker to be careful not to exceed the time limit. Title of the first presentation is Negative Dielectric Properties of the Rhenium N-type Gallium Arsenide Metal Semiconductor Type Structure. Now I will turn the floor over to this section first speaker, who is Esra Evcin Baydilli from Hakkari University. Are you here, Esra?
Yes, I am here. I sent my video. There is my video now, or I will present.
Yes.
Again. Am I start?
Yes, yes, yes.
Please.
You can start presentation.
Yes, okay. There is a problem. Sorry. Yes, here. Huh, okay. Am I now present, or we will watch my video?
No voice.
Hello, dear colleagues. My name is Esra Evcin Baydilli. I am a research assistant at Hakkari University, Faculty of Engineering, Department of Electrical Electronic Engineering. By the end of my presentation, you will have information about the negative dielectric properties of the rhenium N-type gallium arsenide MS structure. My talk will be in 3 parts. In the first part, I will give some information about MS contacts. Then in the second part, I will talk about preparing process of the sample. Finally, I will go on to talk about results and discussions of the negative dielectric properties of the rhenium N-type gallium arsenide structure. Now, I will start my first part of my presentation. Now on the slide, you can see MS structure and MS junction diagrams. Metal semiconductor structures can be thought of as a parallel plate capacitor, since charges form positive and negative regions after the contacts in metal semiconductor contacts. Therefore, the CV measurements of the MS structure give us important information about the MS contacts. We know that capacitors are devices that store electrical energy as an electric field. Considering that the energy storage capacity is calculated with you can see left side of the slide equation, with this equation, and it is seen that the increase of the increase in this capacity is possible with the increase of the dielectric constant of the material and the diode area. But given that there is a limit to increasing the diode area, it's clear that the energy storage capacity of a capacitor depends on the dielectric properties of the material. This situation shows us the importance of studying the dielectric properties of MS structures. For these reasons, in this study, the negative dielectric properties of rhenium N-type gallium arsenide metal semiconductor contact were investigated using complex permittivity, real epsilon prime and imaginary epsilon double prime components. The characteristics of the complex permeability are obtained using capacitance and conductance measurements at room temperature at 1 megahertz frequency, and the voltage range is -7 volt and 6.5 volt. Now I continue my presentation, preparing process part, methodology. The ohmic contact, the MS contact shown in the figure has been prepared by the following the steps shown in the left side of the slide diagram you can see. First, the N-type gallium arsenide substrates were cleaned with the cleaning method frequently used in the literature. Then the gold metal with high purity was deposited on the back surface of the N-type gallium arsenide substrate by thermal evaporation method. The thickness of ohmic contact is 200 nanometers. For low resistivity, 450 centigrade degrees heat treatment has been applied about 5 minutes. Finally, high purity rhenium was deposited on the front surface of the substrate using the pulsar laser deposition technique. The thickness of the rectifier contact is 200 nanometers. The contact area is 177 10 to -4 centimeters square. Thus, rhenium N-type gallium arsenide MS contact with native oxide layer was prepared. Now I continue my presentation, results and discussion parts. Firstly, you see the first graph, which shows the voltage dependent variation of the dielectric constant epsilon prime at room temperature and at 1 megahertz frequency. The dielectric constant values were obtained using the equation, you can see right side of the slide again, from the CV measurements. If we look at the graph, it's seen that the values of the dielectric constant epsilon prime are strong function of the voltage. It can be seen that the value of epsilon prime increases with the increasing voltage up to almost 0 volt. Also, a very little change is seen in the range of 0.14 volt to 0.89 volt in the depletion region. After 0.89 volt, a rapid decrease is observed. This is due to the special case of interface states. When the forward voltage increases, the capacitance value reaches its maximum value and then decreases rapidly and takes a negative value in the accumulation region. Therefore, a similar situation occurs in the dielectric constant values. This inconsistent behavior in the depletion and accumulation region of the dielectric constant is due to the interfacial states localized at the metal semiconductor interface, surface, and dipole polarization and the series resistance effect. Now we will talk about the dielectric loss parameter. This graph shows the variation of dielectric loss epsilon double prime of the sample depending on the voltage. Dielectric loss, we know that is the energy consumed by converting into heat in the material. By using conductance measurements and using the equation seen right side of the slide, we calculate the dielectric loss values. As can be seen from the graph, an inverse behavior is observed between the dielectric loss and dielectric constant. It's observed that the dielectric loss value decreases with increasing voltage in the inversion region. A banding occurs from 0.2 volt and a rapid increase is observed in the accumulation region after 0.4 volt. Again, this inconsistent behavior in dielectric loss is attributed to the interfacial states localized at the semiconductor interface, surface and dipole polarization and the series resistance effect, as well as the dielectric constant. Up to now, if we make an evaluation for both graphs, as it is known why the capacitance value decrease in the accumulation region, the conductance value increases rapidly. Considering that the dielectric constant is calculated from the capacitance value and dielectric loss is calculated from the conductance values, the relationship between dielectric constant and dielectric loss is expected to behave similarly to the relationship between capacitance and conductance. Our results show us that also. In the literature, low or negative dielectric constant values in the accumulation region and the high dielectric loss values are attributed to the addition to the internal impedance of the device. Now, my presentation, last graph. Sorry. Yes. Yes. This graph shows us the variation of conductivity in the 1 megahertz frequency according to the voltage. If we look at the graph, it's seen that the conductivity values of the sample are small in the inversion region at applied reverse voltage. It's seen that the conductivity increases rapidly when it passes into the depletion and accumulation regions at the forward bias voltage. Here, the decrease in the capacitance values and the increase in the conductance values in the accumulation region, or in other words, the decrease in the dielectric constant and the increase in the dielectric loss values indicate a conductive behavior of the sample in the accumulation region. That is the minimum value of the capacitance in the accumulation region corresponds to the maximum value in the conductance accumulation region. That's all. That concludes my presentation. Thank you for your attention. I will be glad to answer your questions.
Thank you, Esra. Are there any questions? We don't have any question. Thank you again.
Thank you again.
And second speaker is Ahmet Kaymaz from Karabük University. Title is Negative Capacitance in the Forward Bias Region in the Rhenium N-type Gallium Arsenide Structure. Are you here, Ahmet Kaymaz?
Yes, I am here, Doctor. Hello.
Hello.
How are you?
Fine, and you?
I'm fine, thank you.
Please share your presentation. Yes, okay.
Please, you can share my video presentation. Dear Congress organization team and dear participants, my name is Ahmet Kaymaz. I am an assistant professor at Karabük University, Faculty of Engineering, Department of Mechatronics Engineering. Today, I would like to give you some information about the negative capacitance behavior of a metal semiconductor type structure with a Schottky contact rhenium. It's known that Schottky diodes or Schottky structures are obtained by the tag contact of the metal and semiconductor materials, with or without oxide, insulator, organic, or ferroelectric interfacial layers. Also, these structures represent the foundation of many semiconductor-based electronic and optoelectronic devices, such as transistors, photodiodes, and solar cells. Oxide, insulator, organic, or ferroelectric layers can be grown as an interfacial layer between the metal and the semiconductor materials by a natural or deposit method. There are many methods used to deposit the interfacial layer, such as spin coating, electrospinning, and sol gel techniques. That some of these methods can be seen in the figures. Consequently, we didn't grow any interfacial layer for this sample, but it can be said that there is a natural oxide layer between the metal and the semiconductor materials. By the way, I would like to mention an important point. If the thickness of the interfacial layer is thinner than approximately 50 nanometers, this structure can be used as a diode and are often referred to as Schottky type structure or diode due to the important work presented by Walter Hans Schottky. On the other hand, if the thickness of the interfacial layer is greater than 50 nanometers, this structure is called a capacitor rather than a diode. Such devices connect supply any carrier transport at a mass interface, and hence they store electric charge and electrical energy. In the light of this information, it can be said that the thickness of the interfacial oxide layer for our sample was calculated as 16.4 angstrom using high-frequency CV data, and therefore this sample can be used as a diode. Why did we choose gallium arsenide as a semiconductor? Gallium arsenide is a semiconductor that has a wide and direct band gap, high saturation velocity, and high carrier mobility. These properties make it highly suitable for fabricating MS-type Schottky structures and also make gallium arsenide preferable as a semiconductor.
No voice, Ahmet.
There is a problem in my
Yes.
video presentation.
Yes, okay. It is
If you want, I can share my video presentation. Fluctuations, such as metal semiconductor-based electronic devices found on satellites. Therefore, the high melting point and thermal stability of rhenium make it suitable for use as a metal contact. Fabrication process. The fabrication stages of rhenium and gallium arsenide type Schottky structure can be summarized that the first step of the fabrication process is the chemical cleaning of gallium arsenide type semiconductor wafer. At this stage, the gallium arsenide wafer was immersed in some organic solvent mixture and deionized water. After this stage, to obtain ohmic contact, highly pure gold was thermally evaporated onto the back surface of the N-gallium arsenide wafer in a high vacuum system. And then rhenium with 99.9% purity was quieted onto a front side of the substrate using the pulse laser deposition technique. So, the fabrication process of the rhenium and gallium arsenide type Schottky structure with a native oxide layer was completed and ready to perform CV measurements. A three-dimensional representation of the MS-type Schottky structure that we have produced can be seen in the figure. To obtain CV data at 1 MHz frequency, it was used Hewlett-Packard impedance analyzer. The schematic diagram of the measurement system can be seen in the figure. As seen in the figure, the measurement was carried out in the cryostat to eliminate the external effects and noises. Of course, the following questions may come to mind. Why measurement was performed at 1 MHz frequency? The reason can be explained as follows. The charts at surface states or traps can easily follow the AC signal at low frequencies, that is, at frequencies below 500 kHz. These charts or traps can yield an excess capacitance and conductance which depends on frequency and lifetime. However, at enough high frequencies, that is at frequencies of 5 kHz or greater, these charts follow the AC signal, and so their contribution to the measured capacitance and conductance can be negligibly small. Therefore, CV measurement was carried out at high frequency for the reliability of measurement and its results. The typical behavior of CV characteristics of MOS devices is as shown in figure. In this figure, three regions which are well known in the literature are seen, namely inversion, ablation, and accumulation regions. However, these figures can be divided into 5 regions, which are strong accumulation, weak accumulation, ablation, weak inversion, and strong inversion. In the ideal case, the value of capacitance is almost independent of voltage in the strong accumulation region, whereas it becomes a weak function of frequency in the weak accumulation and inversion regions. However, due to the ablation of accumulated charges and the presence of surface states, the capacitance value is frequency dependent in the ablation region. On the other hand, CV characteristics of MS-type structures may show a concave curvature or negative behavior in the strong accumulation region due to the effect of series resistance, interfacial layers, and surface or dipole polarization. As can be seen in figure 1, the CV plot has anomalous peak behavior at about 0.5 volts in the forward bias region, and an intersection occurs at about 4.2 volts, and then capacitance values become negative after this intersection. This abnormal peak was attributed to surface state bounce by some researchers. However, recent studies have shown that this may be due not only to surface state, but also to the series resistance of the devices. On the other hand, contrary to the forward bias CV characteristics, the conductance characteristic, which is given in figure 2, increases with increasing bias voltage and reaches a maximum value at the strong accumulation region. In other words, the conductance characteristic increased rapidly and reached its maximum value, while the CV characteristic reached its minimum value in the strong accumulation region. It is known that this situation is caused by the inductive behavior of the MS-type structure. As a result, we can say that the negative capacitance phenomena can be attributed to series resistance and surface states, as well as minority carrier injection. That is, due to the injection of minority carriers, germanium and gallium arsenide type structure exhibited an inductive behavior, and so the negative capacitance phenomena occurred in this device. You can see the references of the presentation on this page. Thank you for listening to me. Dear colleagues, I wish you success in your works.
Thank you, Ahmet.
Thank you, Doctor.
Are there any questions? We don't have any question, but there is have a time for 30 speakers. Professor Şemsettin Altındal is here. Thirty speaker, Professor Şemsettin Altındal from Gazi University in Ankara, and the title of On the Original Solar Power and Energy Losses in the Photovoltaic Solar Cell. Are you here, Professor?
Hocam bir teknik bir arıza olmuş da hani onunla ilgileniyor şu anda.
Yes.
Çok sorry.
We have time to start 30 presentation.
Tamam. Kamera açık kalmış. Neyi paylaşacağız hocam? Konu şurada aşağıdan. Yüz Şemsettin'den.
Welcome, Professor Şemsettin Altın.
I am here.
Yes. Share your presentation.
Yes. 1 minute. Tamam. Şifre mi? Kasma. Tamam. There is a problem. maybe it may be take at about 3 minutes.
Okay. There is no problem. You have a time.
Yes, okay. I'm waiting for you. Oh. Oh, sure.
Yes.
Yes.
Okay.
Okay. Okay.
Yes.
My name is Professor Dr. Şemsettin Altın'dan. Hello, everybody. My presentation on the origin of solar power and energy loss in the photovoltaic. The main scientific and technical problems of the photovoltaic solar cell are relevant to the increase of performance or efficiency of them and reduce the energy losses within the integrated PV modules. This is a more important problem. In general, the efficiency or structural and current conduction mechanism in this device, photo cell or photodiode, or metal semiconductor type Schottky barrier diode with and without an interfacial layer are depend on many factors, such as the procedure of surface process, both the barrier height and the interfacial layer inhomogeneity at metal and semiconductor interface, the concentration of the level concentration of donor or acceptor atoms, temperature, density of interface or surface states, series and shunt resistance, and applied bias voltage or electric field. The first silicium-based solar cell was invented in 1984, which is an important piece of the universe space development, and then it has been industrial commercialized in large scale towards the end of 20th century. Although the cost of solar cell have been considerably reduced due to the fact that the conversion efficiency increases drastically due to introduction and application more sophisticated technology, but the production cost of them is still high when compared with conventional fossil fuel-based technology. Because high conversion technology are usually involve novel design solar cell, optimization of the light absorption, effective collection of photo-generated electron hole pairs, reduction the electron area, and so on. An important fact that, on the other hand, an important fact that is the production and consumption of energy is one of the most important criteria of the developed countries. Therefore, the end of fossil fuels now definitely in sight, we need to find a new major and long-term source of energy. Why solar energy? Sun, it is well known, sun is an enormous energy source, and its source temperature is about 60,000 Kelvin, whereas inner parts of it is around 8 or 40 million Kelvin. Therefore, the source of solar radiation occurs via nuclear fusion under high temperature and pressure in the inner parts of the sun. That is, we are forming a new nucleus through union of small nuclei such as the hydrogen, deuteron, and alpha particles. The loss in mass compared to masses of nuclei turns into energy. On the other hand, that global warming increase in its strength and fossil fuels are depleted day by day, prompt researchers to new approach, new quests. Due to its chemical feature and greenhouse effects, carbon dioxide will not lead to increase in the temperature of world and create much bigger problems in future. Today, the only way to overcome this problem is to make sufficiently use the solar energy, and it is a special energy source which does not permanently cause an environmental harm, and it's ways to utilize it by us. The renewable energy solar cell, fuel cell, or Windows energy is an important alternative energy strategy due to following reasons. Because sun is about 150 million kilometers away from Earth, and it's considered as spherical gas formation having 130 million kilometer diameter. However, the average energy that reaches from sun to Earth's surface is about 10 to 24 joule per year, which is the energy amount of that reaches from sun to Earth only at 1 hour. In addition, the energy amount reaching from sun, which is considered as the endless energy source to Earth per year, is about 150 times larger than the energy amount that can be obtained through Earth's available coal rivers. As a result, radiation energy, the sun, is maintained by the nuclear transformation of chemical elements occurring in via sun's interior at the temperature of many million degrees. This energy can be transferred to electricity by the way of solar panels. In addition, these panels can be transferred and assembled easily modified according to energy need. But the disadvantage of solar panels at the present time, they exhibit low productivity at about 20 or a high initial cost and are not suitable for storage device such as battery. Although sunlight contains a huge amount of energy, a solar cell is very inefficient and can only utilize a small portion of this energy. For example, because some of photons do not contain enough energy to form an electron pair, so they will simply pass straight through the cell without affecting it. Others, however, have too much energy, so they will form an electron pair, but the extra energy will be lost unless there is enough to release to pairs. These two effects alone are responsible for the loss of roughly per 70 of the radiation energy that passes through the cell. Therefore, over the past years, scientists have been developing technology that allows us to capture and convert this energy from the sun to provide heat and electricity. Where does the per 67 and 18 of energy or loss go? It about a for 5 this solar gas converts to heat. The second per 18 of the photons pass through the solar cell without absorption. The last per 2 of energy is lost from local recombination of newly created holes and the electrons. Is a theoretical limit for silicium-based solar cell is about 13. That is lost from the best production cell efficiency is about per 24. The reflected sunlight from the surface of the cell and some losses at the junction of the silicium with electric contacts. What are a strategy to exit the per 30 efficiency limit? First, use more than one semiconductor material in cell, like multi-junction solar cell. Use more than one junction in cell, tandem cells. Sunlight can be converted at about 500 times using the inexpensive lenses. And a combination of PV semiconductor with the heat-based technology to harvest both forms of energy or use quantum dots to harvest some of this excess photon energy for electricity.
So, sorry, Professor, 2 minutes left.
Yes. The other some important of them reduce the energy loss, the excess of impurity in semiconductor, effect of temperature, high damping level, and the duality factor, series and shunt resistance, oxidation or surface state, and the other presentation will be the conduction mechanism of these solar cells are dependent, such thermionic emission, thermionic field emission, generation recombination, multi-step tunneling via interface trap or surface states, Gaussian distribution of barrier height, compete usually one of them may be dominant over the others in a certain temperature and applied bias voltage range. On the other hand, the simulation contribution from 2 or more current condition mechanisms could also be possible among the tunneling mechanism. How solar cell work operates? Solar cell in an electronic device that converts the energy of light directly in the DC using the photovoltaic effect, first to form an inner electric field in the junction after diffusion process, and second create electron hole pairs near the junction under illumination intensity. The process of conversion first requires a material which absorbs the solar energy and then rises the electron to higher energy states and then follow this high energy electron to an external circuit. The other some PowerPoint of them, the schematic diagram of the simple phased solar cell and cell modules or array. The other figure, the equation circuit of solar cell, as you can see here, is dependent on both series shunt resistance of this device are more effective on the efficiency. By using anti-reflection quantum material, the efficiency, the reflection of some proton can be offset. Electric characterization of Schottky barrier. Usually we, in my laboratory, we use VPF chrostat with 4 optic windows and use cat day measurements and HP impedance analyzer both in the chrostat condition and the area. And so that thanks for your attention.
Thank you, Professor Şemsettin. We have no time to ask question. Thank you.
Thank you.
Yes, another presentation title as
Canan.
Effect of filler on shape memory performance in nanocomposite material with polyvinyl alcohol matrix. Canan Aksu, Can Bey, Nihan Ünlü from Fırat University in Elazığ. Are you here, Canan or Nihan?
They are not here, ma'am.
Okay. Another presentation title is Thermal Analysis of White-Based lead on Byzantine Film-Coated Aluminium Substrate in Harsh Ambient. Abdulkerim Hamza El-Laden, Shanmugan Subramani from Nano-Optoelectronic Research Laboratory in Malaysia. Are you here?
Yeah, I'm here.
Yes, thank you.
You can go ahead with the video. Already sent a video.
Yes, share your video. Okay, and then start, please.
I've sent you the video.
Yes, just a moment. Yes, you can start presentation.
My name is Abdulkarim Hamza El-Laden, a PhD student from School of Physics, University of Science, Malaysia. I would like to present my paper titled Thermal Analysis of White-Based LED on Boron Aluminum Nitride Thin Film Coated Aluminum Substrate in Harsh Ambient. The essence of the whole work is to develop a robust and low thermal resistance material that will be able to mitigate the accumulation of heat at the junction of an LED for patient performance, longer operational life, and higher luminous flux. Abstract. Using thermal transient testing method and cumulative structure function analysis, the thermal analysis of high power LED mounted on aluminum substrate, bare aluminum substrate, and coated aluminum substrate at 3 different bond line thicknesses and at harsh ambient temperature of 55 degrees C with high driving current of 700 milliamp is carried and presented in this paper. The bare substrate for thermal resistance performance was found to be in the range of 12 degree Kelvin per watt, while the coated substrate is found to have reduced the total thermal resistance of the LED package from 12 degree Kelvin per watt to 7.9 degree Kelvin per watt. And also the junction temperature is reduced to about 20% from the the junction temperature with bare substrate. The rating curve for the LED is also established using the Terra-led view software and material presence. The ground material is confirmed by XRD and FTR analysis, as will be seen in the figures shown in the slides. An introduction: 15% of global electricity use goes to lighting. That's residential, industrial, and street lighting combined, corresponding to the combined electricity consumption of Russia, France, Australia, Indonesia, and the UK. The continuous demand for light-emitting diode as retrofitting option for inefficient incandescent bulbs, fluorescent lights, CFLs, halogen lamps for building and street light is on the increase. And according to Sustainable Development Scenario, light-based lighting is expected to become the most dominant light technology of the future, surpassing all conventional lighting technologies driven by its age with respect to service life, energy efficiency, versatility, and lower cost. And on the other hand, performance, reliability, and lifespan is affected by accumulation of excessive heat generated within the LED, resulting from high junction temperature buildup due to higher current increase for higher luminous flux. Thus, the need to develop a robust low thermal resistant solid thin film is necessary. Now, these two graphs represent the Sustainable Development Scenario 2010-2030 for LED, for lighting cells, both for light emitting diode, fluorescents, incandescent lamps, halogen, and what have you. On the left side, you can see clearly the LED as of 2010, the cell is very low, just about 1% compared to higher, percentage of fluorescent wood cell, about 35%. And then other lights, that is the incandescent, the halogen, and what have you, that were able to sell up to 65%. You can see clearly here it's up to 65%. And then the LED rose to about 46% in 2019, while fluorescent and other lighting points are dropping down. And LED is expected to reach about 90% by 2030, while the remaining technologies are expected to go down, some to 0 and while some to 12%. However, on the right-hand side, you can see the typical efficacy of different lighting technologies: LED, linear fluorescent, compact fluorescent, halogen, incandescent. Among all of them, LED, is the one, right? The luminous efficacy is continuing increasing. From 2010, it was 68 lumen per watt, and it rose to 103 lumen per watt by 2019, and is expected to reach 163 lumen per watt by 2023, while others remain where they are. Our work actually is to, as I earlier said, is to develop a material that will see the LED technology to reach the projected efficacy and acceptability by the Sustainable Development 2030, and the challenges in that is overcoming the challenges in performance, reliability, and operational life. And then second part of that is the temperature buildup is considered the most influencing factor in lowering the energy conversion efficiency. And then the junction temperature buildup is largely influenced by thermal fat. That is, if the thermal fat is very poor, then the heat will be accumulated and will not be, dissipated easily. And then ambient temperature within which the LED is operating, and then higher driving current. Technically, there is need to modify the thermal fat by developing a robust solid thermal interface material with low band line thickness that can mitigate and dissipate heat effectively at harsh ambient, that is a combination of high current density and high ambient temperature within safe operational limit of the LED to improve its performance. Now, the thermal fat improvement in this work is achieved through the smooth surface filling of aluminum heat sink with low thermal resistant aluminum nitride boron composite grown using sputtering technique for total or partial displacement in air in the gaps between the heatsink and the LED surface as illustrated in the figures below. The figure on the left, you can see this is the LED at the top and this is the heatsink. If you look at the surface of the two contacting bodies through a microscope, you see that they are not smooth, they are rough. They have gaps, wavy surface, and the gaps created between the two surfaces is occupied by air, and air, is a very high thermal resistant material. So therefore, it has a little, very low conducting capability. If you look at it, the heat is conducted only through the points where the two were able to meet, like this point, and this point. And the removal of heat is not efficient. And based on our work, we now try to fill this gap in order to, create a much better contact point. Like in this image on the right side, this is our material. We coated, to the extent that we're able to get a smooth surface so that the contact area between LED and the heatsink is now increased. Therefore, a good, faster way of dissipating heat is attained. Results: thermal resistance, improvement in thermal resistance from 12 degree Kelvin per watt based on bare substrate to 7.9 degree Kelvin based on coated substrate is reported. Junction temperature reduction, junction temperature from 27.34 based on coated substrate to 17.34 based on coated substrate is also reported. And then using thoroughly view software, the operational parameter for LED based on coated and bare substrate is established on, at 0 to 1050 milliampere current range and maximum temperature of 135 degrees C as dictated by the data sheet of the LED. The LED indicated that the junction temperature of the LED should not go beyond 135 degrees C. Now, thermal resistance. This is a graph of our thermal resistance portraying 3 different layers of coated material and uncoated material, uncoated substrate. The uncoated is the blue, as you can see at the extreme end, extreme right, and then we have the black, the red, and the green. They are all coated with different thicknesses. And this graph gives us the opportunity to understand and optimize the best thickness, monoline thickness that is supposed to be used based on the substrate and the material itself. And then this is the junction temperature, and if you can see clearly, it's showing similar pattern. The black is the lowest in terms of junction temperature, followed by the red, the green, and then the bare substrate. The rating curve here is indicating that the coated substrate is colored red, and then the bare substrate is black with 11.7 degree Kelvin per watt, while the coated substrate is the thermal resistance about 7.5 degree Kelvin per watt. This is simply showing that the LED using the coated substrate can perform at 1050 milliamp up to within 113 degrees centigrade safely, while it can only perform safely on the bare substrate at 90.9. And then if it goes down 800, this is the result for 800, this is for 600, this is for 400, and this is for 200 milliamp. You see at 200 milliamp, the LED on the coated can operate at 130 degrees C, and it can operate on 126 degrees C on the uncoated substrate. These are the two images of the, this is the XRD image, and this is the FTR image confirming the presence of the grown material. In conclusion, the grown material is observed to have reduced the total thermal resistance of the LED's thermal path to a reasonable degree, and that is seen to have affected the junction temperature, dropping by about 20%. The improvement in the operational parameter of the LED within safe limit is also reported in the last rating curve graph shown before this slide. And all these improvements were achieved at harsh ambient condition of 55 degrees C. Acknowledgement, I would like to appreciate the organizing committee of the IHEC 2021 under the chairmanship of Prof. Dr. Yasmin for giving me the opportunity to present my result at the Congress. Thank you and God bless.
Thank you, Abdulkerim Hamza, for your presentation. Are there any questions? There is no question. Thank you again. Another presentation. Shift bus derived from two amino thiophene synthesis, characterization, and electrochemical behavior. Ayla Balaban Gündüzalp, Damla Akkaya, Ebru Erdoğdu, Serhat Mamiş from Gazi University, Naki Çolak from Hitit University in Çorum. Are you here?
They are not here hocam.
Okay. Finally, the last presentation in this section. The title is Tuning of the Optical and Electrical Properties of Copper Iron Oxygen by Cobalt Doping. Anantu Paul, Mohammed Nasir, Rini, Kumar Misra, Somaditi Sen from Indian Institute of Technology, Indore in India. Are you here?
They are not also here, ma'am.
Yes. What can I do? Now, thank you. I am very grateful to all of you for your contribution and interest in this section. I hope that this Congress will be beneficial and successful for everybody. Thank you for all participants. Ebru Erdoğan.
Ebru Erdoğdu.
Yes, excuse me. Let's share your presentation.
I am Ebru Erdoğdu from Gazi University. Shift basis there from shift bases there from 2 amino thiophens synthesis, characterization, and electrochemical behavior. In this work, we synthesize shift bases using amino thiophan, amine and aldehyde react with each other, then shift base forms ure, NMR, hydrogen NMR, carbon NMR techniques are used to determine chemical structure of these compounds. Electrochemical behavior of the compounds were investigated using CV. Aminothiophens uses included pharmacology dyes agrochemical applications. Thiopen derivatives show diverse pharmacological, antimicrobial, antioxidant, anti-tumor dyes, agrochemical applications. These compounds are used to contract natural products, dyes, agrochemicals. 2 aminothiopen derivatives are known to serve as kinase inhibitors. Compound 1, synthesis of this compound. Compound 1 synthesized by Gavel's method. Compound 1 has this melting point and has this percent yield. For compound 2 and other ones, dissolved ethanol and added dropwise with constant stirring. The mixture was refluxed and dissolved in ethanol and crystallized. Compound 1 has these chemical shifts.
Tamam. Hocam YouTube'a geçtim. Şimdi kaydı başlatıyorum.
And for
Olur mu Gülay hocam? Tamam. Şimdi katılımcıları alıyorum. Artık
carbon NMR has these chemical shifts.
Watch my
Compound 1 shows this stretching and bending vibration. For compound 1, molecular ion peak is number percent yield 100% yield.
By the way, actually,
For compound 2, hydrogen NMR has these chemical shifts. We understand shift base for forming these chemical shifts. And we understand shift bias as forming imine group. Imine peak shows the formation of shift bias compounds. Aromatic protons are the range of 7 and 9. For carbon NMR, the azomethyl carbon is observed at this chemical shift. Imine stretching vibrations was observed at this number. Other vibrations are observed at this way.
We are formed without absorption. The last
material with polyvinyl alcohol.
I've sent you the video.
You can
Radium shaped glove material difference.
For compound 2, molecular ion peak was observed.
Is advancing service life energy efficiency percentage. Result in cameras.
For compounds,
Was for light emission diode.
for other compounds, hydrogen NMR.
Continue them down while LEDs would activate halogen when they can lower estimated current but any erupted high system.
Like the other compound 2, and this compound has imine group vibration.
This level is about 10 that the E substrate
Molecular ion peak.
simple. Yes, God bless.
answer for your presentation. Another presentation of chemical Kaya Gazi in Çorum. Are you here?
Table electrochemical behavior. Electrochemical behavior of the compounds were investigated using cyclic Voltaire CV. Shift base shift bases have additional peak. Imine groups reduction shows the formation of shift bases from omnithiophane. Shift bases have many industrial application types as pigments and dyes, catalysis application, polymer stabilizer. Shift base complexes are widely used for industrial purpose and also exhibit a broad range of biological activities than free ligands.
finish your presentation?
Yes.
Yes. Are there any questions? No. Can I ask a question? Did you measure yield? This substance. Yield.
Yes. Yield.
What the values of the yield? You know?
Yes. For compound one or others, which one?
Two aminothiophene.
For compound two.
Shift bus 1, 2, 3. Please say me one compound, for example.
One compound. For
Yeah.
example, for one compound, 73% yield.
73. It is good or not for you? Good or not for you?
Good.
Good. Thank you. Thank you. Okay. The last presentation we see from Ebru Erdoğdu. Thank you for presentation, Ebru. Now, again, the last presentation, title is Tuning the Optical and Electrical Properties of Copper Iron Oxygen by Cobalt Doping. Are you here? No. From Indian Institute of Technology, Indore, in India. That's enough. Thank you for your contribution and interest in this section. Okay, thank you.